Hello, hello, hello. We got some rings to talk about, right? And it's kind of like they say, if you like chemistry, put a ring on it, right? So here we are talking about rings. So in the previous video, we talked about the three-member ring, and it turns out to be the case that only two electrons favors the population of the bonding orbitals of the three-member ring. And so it turns out to be the case that three-member ring has to be cationic to be aromatic. Now we're going to see what's the story for the four-member ring. And just like what we did in the previous video, we place one of the vertices pointing straight down on the circle. This is the Huckel circle. And what you see right here is basically, how many levels you're going to have as you go from top to bottom. So here you have one instance of touching the ring on the very bottom of the polygon. On the next instance, you have two instances of touching the ring at the same level. And then you have one last instance of touching the ring on the very top. So we're dealing with a molecular orbital that's going to look like this. One lower energy level, two middle energy levels at the same level, and then one last higher energy level. And as far as the molecular orbitals, just like we mentioned in the previous video and also the conjugated alkene video, when you go from lower energy to higher energy, you are increasing the number of nodes that are present on those orbitals. So the lowest orbital will have no nodes, meaning that all the p orbitals are in phase with each other. The next set of orbitals of the same level will have to have one node. In one instance, the node is going to be basically from top to bottom, and the other instance will be from left to right. And then the last orbital is the one where you're going to have all the p orbitals alternating, so you have a total of two nodes in the system. And like I mentioned before, it is easier to look at these diagrams from the top-down view, so that you don't have to, kind of deal with the both lobes of the p orbital. So a better way to kind of look at it is just from that point of view, the top-down view. So for this orbital down here, we have all lobes on the top portion of the molecule shaded. On the other ones, we have two on the left are unshaded, the two on the right are shaded, so the nodes passes right, through the middle of the molecule from top to bottom. And then over here we have the top two that are unshaded, the bottom two that are shaded. So the node passes through the molecule from left to right. And the last one, as you can see, you alternate the shading of all the orbitals. So you have two nodes, basically like a cross, present in a molecule. And that's how these molecular orbitals are meant to, be depicted. So personally, I would recommend you just go based on this top-down view. It's a lot easier to kind of, make the drawings and see what's happening. All right, so now as far as the aromaticity is concerned, yes, you do want to end up filling up all the orbitals that fall below the middle line. But if you do have orbitals that literally fall on the middle line itself, then you can also populate them to no detriment to the energy, the overall energy of the molecule. So you could make this aromatic, this four-member ring aromatic, if you only populate the lowest level, which will be two electrons, right? And because you have four carbons in that ring, that's four p orbitals, which is four pi electrons. If you only populate the lowest level, for you to be aromatic, then you have to get rid of two electrons, right? So one way that you could make this happen is if the four-member ring was a 2+ cation, right? Remove two of those electrons and you will ensure that only the lowest level is populated. But you have another option. And that option is that in addition to populating the lowest level, you also populate the two levels that are at the neutral ground, the non-bonding orbitals. Not anti-bonding, not to be confused with that. These are non-bonding. They don't, give you lower energy nor higher energy. So they're basically neutral. So if you populate those two levels, and what I want you to also notice is that you don't populate them partially, right? So there shouldn't be any ampere electrons here. If you populate them all and completely, like two electrons for every single level. So what that will basically mean is that we're going to bump this up to 6. And you might start kind of noticing that, the fact that every single time, we're going to be seeing as we increase the number of the carbons that the polygon contains, we're going to be increasing the number of these two energy levels that keep popping up at the same energy state. So we're going to end up increasing the value of electrons by 4 electrons. And ultimately, this is where the 4n plus 2 rule comes from. This will become more clear as we, move into the bigger polygons. So, needless to say, this is 6 electrons. 4 carbons means 4 pi electrons. So for this to be true, we will have to end up with the anionic version of the cyclobutadiene ring, technically speaking. If you end up putting 2 more electrons on it, this is dianionic, but it will be aromatic as well. All right, so we're going to take that framework further. Now we're going to look at the 5-member ring. And just like before, you're going to make sure that one of the vertices is pointing straight down on the circle. And as such, what you should see is that the energy levels will be 1 on the lower level, 2 on the next level, and then another 2 on the top level. And so here it's even more clear that yes, as you go from from the lowest level to the next level, and then from that level to the next level, you are increasing the number of electrons by 2. Excuse me, not by 2, by 4. By 2 orbitals, but by 4 electrons altogether. So the middle ground is this part right here. And here are the orbitals with the p orbitals shown very well. But like I said, it is better to look at this thing from the point of view of just the top of the molecule altogether. So just the top lobes of that p orbital. And if you do that, then you should see clearly that the lowest molecular orbital has no nodes. The next two happen to have one node. Well, they don't happen. They have to have one node for this to work out. And I want you to acknowledge also that the left version and the right version, they're different molecular orbitals. They're not the same, right? One of them has the node passing through one of the actual p orbitals, meaning that that p orbital is completely, nullified in the molecular orbital, but the other one has the node passing through the bonds, so none of the p orbitals are affected in terms of being present or not. They are different molecular orbitals, but they only have one node, so they're the same energy state. And then the last one has 2 nodes, one that's basically across, and you have to go through one of the p orbitals, the other one that goes through the bonds, but still gives you 2 nodes altogether. So as far as ensuring that this is aromatic, you just want to make sure that only the lower levels are populated. And in this case, there is no set of energy levels at the mid ground, right? We only have the 3 on the bottom. So that would mean you need 6 electrons. So if you think about it, a 5-member ring means 5 pi electrons. So for you to end up with 6 will mean that you will have to add 1 additional electron to the system. So in reality, for this 5-member ring to be aromatic, you will have to make it monoanionic, right? You'll have to accept an extra electron. And if that's the case, then this 5-member ring will be aromatic. All right, now we get to the familiar picture that you've seen in the past, the 6-member ring, which is going to be your benzene ring. And like all the other examples, the vertex is pointing at the bottom portion, only one of them. So this will show you a pattern that is 1, 2, 2, and 1 as far as the times when you touch the ring. And the middle ground is right here. So we're going to end up populating only the 3 lower levels again. All right, and here are the regular molecular orbitals, but here are the better way to look at it from the top-down view, right? Lowest orbital, no nodes. The next 2 of the same level, only 1 node, but alternating in where the actual node's located. The next 2 have 2 nodes, and the last one has 3 nodes in total. So that tells you the whole story of these orbitals. And like I just mentioned, you only want to populate the 3 lower levels, which will give you 6 electrons. And for the 6-member ring, 6 carbons equates to 6 pi electrons. So this one is going to be totally neutral. You don't need to add electrons. You don't need to get rid of electrons because you have the same exact number of carbons as you do of require pi electrons to make this thing aromatic. And this is ultimately the main reason why benzene is one of the most well-known aromatic molecules, because out of all of them so far, and technically of the ones that we're about to see, is the only one that happens to have the correct number of carbons for the correct number of pi electrons to satisfy the molecular orbitals. And so it's neutral, right? And if the molecule is neutral, then yeah, you're going to have a much easier time, encountering it in the world of chemistry. All right, we're going to go 2 steps further. So now 7-member ring. 7-member ring, if you place one of the vertices at the bottom, right, you have basically this pattern: 1, 2, 2, and 2 as far as the sequence of molecular orbitals. And the middle ground is right here. So for this one, yet again, we only populate the 3 energy levels below the middle ground. And here I just went ahead and show you the molecular orbitals just from the top-down view, because it gets too ugly by the time you go past these 6 carbon atoms. So no nodes for the first one, 1 node for the second one, 2 nodes for the next set, and then 3 nodes for the last set. Okay, and so we basically, just by looking at this diagram, we just populate the lowest 3 levels, which means that we only need 6 electrons, just like benzene, just like the 5-member ring before. And what that will mean is that, well, we have now 7 carbons, which means that we have 7 pi electrons to begin with. So for this to only end up with 6 will mean that we will have to get rid of 1 of those electrons. So this ring will be aromatic as long as it's monocationic. All right, and then the last one, the 8-member ring, right, which is probably one of the trickiest ones to draw within the circle, with one of the vertices pointing straight down. But if you do that, what you see is that the diagram breaks down as follows: 1 level on the bottom, 2 on the next, another 2 on the next one, 2 more for the second to last, and then only 1 for the very last one, right? So in this case, we do have a middle ground that actually has energy levels touching the middle ground. And like before, no nodes, 1 node, 2 nodes, 3 nodes, and 4 nodes by the time you get to the last, molecular orbital. So here, you basically want to take care of the lowest levels, the ones below the line, which will mean 6 electrons. This is a 8-electron system, or technically an 8-carbon ring. So you have 8 pi electrons. So if you end up with only 6 electrons to make this aromatic, then you need this to be a dicationic system, right? Remove 2 of those electrons. However, because we have the levels that are on the middle ground, you could also populate them, and that will now give you a total of 10 electrons. Since this is an 8-carbon system, that's only 8 pi electrons, so you'll need to add 2 more for this to be aromatic. And normally this is, what you see in this type of rings. But yes, 2 plus or 2 minus, and you got yourself an aromatic ring. Okay, so in the next video, I'm going to show you the true identity of these rings, as they happen to be, presented in the chemical community. So I'll catch you up right then.